can try to create some sort of a function that assigns scores to some span of text and highlight them when the uncertainty exceeds a certain threshold. All right, so now let's maybe discuss a little bit what uncertainty is. I will have more formalized discussion just in a minute, but what we're actually doing when we're saying, oh, we are quantifying uncertainty, we're estimating the confidence of a language model or any model. There are two approaches to the problem of hallucination detection. In one approach, on the top, we have a, let's say, question, LLM generated an answer, then we just run some sort of external fact checkers, some external tools that will tell us, okay, whether there is something fishy or not. And in the second case, when we are doing this uncertainty quantification, what we care about is we do not use any external verification tools at all. Because these tools might be also biased, they might be incomplete. Let's say you're using some knowledge source, this knowledge source becomes obsolete, and et cetera, et cetera. We want to extract as much as possible information from the language model itself. We would like to extract information from its logits. We'd like to extract information from samples of a language model. We maybe can dive into some patterns in attention maps or patterns in their hidden activations. And when I'm trying to explain to the people from industry and generally what uncertainty is and what we are doing, I'm saying that we are trying to extract as much as possible information from signals that come from LLM itself, contrary to other approaches that use some external knowledge source, external LLM to verify the generation. And that's actually pretty well aligned with what I hear from other people who work in this area. Actually, I've been to ICML. I came here from ICML in Seoul, and where we got a presentation of Yared Gal. It's one of the main people in uncertainty area. Well, I mean, like not main, but like the most well-known, I would say, person in uncertainty quantification. And I asked him like directly, what do you think? How we should treat uncertainty? Should we try to formalize this very, very strictly? What is uncertainty? What is not uncertainty? And he said like, oh, actually, uncertainty is everything that helps me to solve some task, reliability tasks, selective generation, or maybe hallucination detection. So I think that this definition, this intuitive definition of that uncertainty is some score that you can extract from LLM itself to solve certain tasks, such as selective generation, selective hallucination detection, is exactly what many people think of in our community. All right. Yeah, and I would like to also note that uncertainty is not something that is it's complementary to other techniques that helps you to deal with hallucinations. Let's say if you have RAG, you also can do RAG, why not? But you also can put uncertainty on top of that and help yourself a little bit more. Just a few words before we dive into like a lot of theory, a lot of methods. Uncertainty helps, what uncertainty is and how it can help us to deal with our day-to-day tasks. Actually, it has a lot of applications, not just selective classification, not just hallucination detection that we will be focusing on during the talk, but there's actually a lot of applications in adversarial type detection. Of course, it's a great way to detect auto-distribution instances. Active learning, if you know what it is, it's like the selective way of annotating the instances in our corpora. It's also useful. Uncertainty is also useful for detecting such instances that are mostly useful for annotation. And recently, we found out that the uncertainty scores, or like something like uncertainty, some supervised confidence estimators, are quite useful for improving efficiency and effectiveness of multi-step reasoning systems, and also helps us to improve the agentic AI agents as well. And we will briefly touch that in the end. Right, so a little bit theory. So what uncertainty is, we'll first start with the classification example and then gradually move to LLMs. So as you probably know that, well, language models and not language models, basically most of the neural networks that we use today, they're equipped with the softmax layer that can produce as some softmax probabilities. And well, we can create an uncertainty score using the softmax probabilities. That actually not a bad idea in general. These uncertainty scores will be a good baseline. But if that will be like the perfect method, of course, there'll be nothing to do for us, right? Our job will be done at this point. So the problem with softmax probabilities is illustrated on this chart. We can have, let's say, 2 moon data set, and we can build a very simple classifier that has this decision boundary. And in many cases, we can find that this classifier would have very, very high uncertainty only on this very low, narrow boundary between classes, and this decision boundary. But it will assume that everything, let's say, here in this area or in this area is confident. So uncertainty only located here. But as you can see, the data that we have in our training data set is located only in this area. So what actually, so our softmax probabilities or uncertainty based on the softmax probabilities would be overconfident in areas where we don't have any data at all, which is obviously overstatement because we don't know how our space, we don't know anything about this area, right? So actually what we really want to have is something like this. So we would like to have a very confident area, like where we have data, and in the areas where we don't have data, we would like to actually express high uncertainty. So that's probably a much better picture than with the softmax probabilities. But softmax probabilities will never give us such a picture. So here we need to talk about 2 major sources of uncertainty, which we call aleatoric or epistemic uncertainty. Well, aleatoric uncertainty is uncertainty that reflects noise in the data. The idea is that even if you have a perfect classifier, there's still impossible to, there's still ambiguity in the data in our task that doesn't allow us to perfectly solve this task. Let's say if some person comes to you and says that, well, I have a high temperature, headache, I have cough, fever, that might be SARS, but that might be also COVID. You cannot make a proper diagnosis with just these few symptoms. To make a better diagnosis, you need more features. You need to also understand whether there's any loss of taste, for example. So in this situation, we have high aleatoric uncertainty. At the same time, there's another source called epistemic uncertainty that reflects the lack of knowledge about our data, about the lack of knowledge about our parameters of our model. So, for example, if you're having just one instance in your training data set, well, that's probably not enough to make a good classifier, right? If you have 2, it's better, but once again, still bad. When you have a lot of data, then, well, probably your classifier knows almost everything about your domain, and then the epistemic uncertainty is low. So in our case with medical diagnosis, it would be asking, let's say, a model that was trained on heart diseases to predict something about lung diseases. Obviously, that will be pretty difficult if there's no training data for lung diseases, and most of the training data is coming from the heart diseases or maybe stomach diseases. So having more data will help us to deal with this problem. We can understand better our distribution of parameters of our model. And so this source is called epistemic uncertainty. And this is a good illustration of this concept, these two concepts. On the left side, you can see a case of high aleatoric uncertainty. Once again, you can see that we have lots of data points here, and at some on the decision boundary, we see the area where we cannot reliably distinguish with two classes due to high aleatoric uncertainty, because like each point might be have ambiguous realization, ambiguous prediction. On the right side, we can see that, okay, now we have much less data, and we are becoming much uncertain about how we can draw this decision boundary. Like on the left side, we can draw the decision boundary in the optimal way, only probably in one way. But on the right side, we can see we can draw this decision boundary in multiple different ways, and that's exactly illustration that we have lack of knowledge about parameters of our model. All right, so yeah, we discussed uncertainty as some sort of like heuristic score that helps us to deal with some tasks that primarily comes from the internal representations of a model, that primarily comes from capabilities of a language model itself. But there's a few, there's two ways of formally defining uncertainty. Well, actually, one of the biggest problems of this field is that it's very ambiguous. Uncertain is a very uncertain term, actually. And when I talk with many people from the field and say some like uncertainty, everybody thinks about this term in different ways. I think that's okay, but I believe that we need a formal definition. So I will try to give you like two formal definitions of uncertainty today, but I just want to emphasize that this is probably not the only way of thinking about uncertainty. But today we will be mostly trying to formalize uncertainty and other things that related to that in two perspectives. The first perspective is through approximating empirical risk. So consider you have a model with some parameters that provides us some approximation of the probability distribution, of real probability distribution. What we can do, well, what we usually do in machine learning, we introduce some loss function that tells us how good is the model on our data, on the test data, on the trained data. This loss tells, well, whether classifier is good or bad. It can be a very simple loss, such as 0-1 loss, when you just add 1 to loss if the model makes a mistake, or you can have something like log loss, which takes into account actually the whole probability distribution of a language model or any model. And well, uncertainty here would be an expected risk of our classifier, which we can measure in this way. In general case, this integral. In classification in particular, we can compute this summation of the over our probability distribution, approximated probability distribution. So once again, from this perspective, when we are trying to quantify uncertainty, we are trying to understand what might be the risk of my classifier on this particular prediction. What is the expected risk of my classifier on this particular prediction? And from the point of, and you can actually decompose the total risk in two components. One component is called bias risk. This bias risk is the minimal risk that you can actually achieve on this data. So if you have ideal approximation of your probability distribution, you know exactly how this data was generated. You still cannot do perfectly on this task because of this ambiguity. So this bias risk is uncertainty related to aleatory component. Yeah, so this bias risk is minimal risk that is possible it doesn't depend on your model. It depends on the true generative process, and that's why we can think about this component. If we approximate it in a perfect way, that will be a very good, the perfect approximation for aleatoric uncertainty. So, and we can, just take total risk and subtract this bias risk, and everything that will be left, it's basically epistemic component that related to this lack of knowledge about parameters of our model. Right, but that's not the single way of thinking about uncertainty. Actually, that definition through the bias risk, through the total risk, is actually very principled in the way that it takes into account various problems that we have with the second definition through the posterior predictive entropy. So according to this definition, let's say we have some sort of approximation of our probability distribution through using our model, and our uncertainty is basically the entropy of our predictive posterior. That's total uncertainty. And that's possible to decompose once again into components. If you do math correctly, you can find out that there's epistemic part, which is mutual information between the distribution of your parameters of your model and your predictive posterior, and aleatoric component that reflects that is basically expectation of the entropy of each of the realizations of your parameters in your model. That's another way of thinking about uncertainty through predictive entropy. And actually, if you define the loss in your definition through total risk and through Bayesian risk, if you define loss as logarithm log loss, then basically these two definitions align together under assumption that your probability distribution that is approximated by your model is very similar to the real distribution. So we can think about these two definitions through the risk or the entropy of the predictive posterior more or less equal under certain assumptions. Yeah, just a few words saying about how we can compute uncertainty for the classification. Well, for the classification, when we have, let's say, some sort of model that gives us probability distribution for our classes, aleatoric uncertainty can be estimated. The best way of estimating uncertainty would be just looking on the probability of our classes, or like the entropy of our classes. That would be probably the best way of thinking about aleatoric uncertainty. For epistemic uncertainty, we need to do something else. We need to actually analyze our distribution of our parameters in our model. So usually people do some sampling. It might be some dropout, Monte Carlo dropout. It might be some ensembling. But what we need to do, we need to investigate the distribution of the parameters of the model to understand how much uncertainty is located there. But again, once again, it's for aleatoric uncertainty classification, think about the entropy of predictive posterior as the best option. And for epistemic uncertainty, think about some Monte Carlo approximations that can be more or less, that can reflect your epistemic uncertainty. Right, so intermediate takeaways from theoretical part. First of all, uncertainty is quite overloaded term. Rather than a single mathematical quantity, I try to give you two perspectives about uncertainty, what we are doing here. We are trying to find a good approximation for our total risk, or maybe Bayesian risk, depending on what your task you're solving. From the second perspective, it's an entropy of predictive posterior. If you have, let's say, Bayesian model, and you have a great understanding of how your prior should look like, your approximation of the real distribution is more or less good, then the perspective, the definition of uncertainty through the entropy of predicted posterior is also kind of optimal definition. So these two perspectives coincide under certain assumptions, but I need to right away tell you that there's a little bit, well, you can think about this, oh yeah, so we have this formal definition, let's now, now we can do everything with that. We can create interesting approximations, we can solve tasks, let's just be Bayesian and everything will work. Well, unfortunately, it's not. In real world, none of these assumptions actually hold. And in our in real world, our knowledge about priors of model parameters probably is lacking. The approximation of the real distribution is also not that close to the real distribution as we would like. So, in fact, in real life, we have to actually develop a lot of heuristics that might have certain rooting in Bayesian theory and decision theoretic approaches. But in fact, many of the techniques that are actually work in practice, they're still kind of heuristics. And today I will present a lot of these heuristic techniques that you will, that have more or less principled background, but in fact, a lot of them actually are still a little bit hand-wavy. Right, so let's move on to LLMs. So before that, we were discussing uncertainty for classification models. But with language models, everything becomes way more sophisticated. First of all, when you're working with a language model, you have not just one single prediction, you have multiple predictions because you're making generations for each token, and for each token you make a prediction from your language model. And these predictions, they're not independent actually, they're conditionally dependent. As you can see, here's a factorization of the probability of your generation according to our regressive language model. So, so the problem with uncertainty for LLMs is that you need to not to just quantify uncertainty for a single prediction, you have to aggregate uncertainties for multiple sequential predictions. And these predictions are actually conditionally dependent. And here's an illustration of why this is a problem. When a language model generates a text, it assumes that everything generated so far is correct. I mean, it comes from its objective function during pre-training. When you're training your language model, you just feed the whole text, the books, you feed the scientific papers, and the model just needs to reproduce everything that it sees during training. So the model basically assumes that everything that it has, everything that it sees on the left of its context is correct. That means if the model generates a hallucination at some point, it will condition on this hallucination and continue with even more hallucinations. So let's say in this example, it generated some hallucination. I think that this Mackenzie Kakwato competed in 2012 Summer Olympics in London. And you can see that probably you can detect this hallucination with high entropy or like low probabilities of these tokens. But after that, it conditions on what was generated so far, and it generates even more hallucinations. Once again here, 2012 Summer Olympics. It's still hallucination, but now it considers it completely correct. So conditional dependency of this process of token generation leads to this problem when after first hallucination, there's basically no way to understand whether um, after first hallucination, you condition on these hallucinations, and you're very, very confident in what you are saying, even even if it is very, very wrong. So the third problem, the third problem is that actually when we are doing generation from a language model, we are using some decoding algorithm. It might be greedy decoding, it might be sampling, it might be some beam search, and it's despite that, let's say greedy decoding and beam search, they usually produce a very good generation with a good probability. They do not produce the there's no guarantee that they will produce the optimal probability. There's no guarantee that it will generate the most probable sequence under this particular model. Moreover, the most probable generation might be not the best one according to the bias risk. Actually, what is optimal might have even lower probability, but it might be located in the distribution area where the density of other generations is quite high. Like you can generate. Well, there's another example here. For example, you can generate like might sample 3 meanings. One of them is like sequence A and have meaning A, but there's like 2 other sequences, sequence B1 and B2, but they both have the same meaning. And in that case, actually, despite the fact that the most probable sequence is A, together the generations from the language model that have maybe lower probability, together they have more probability mass than the first answer. So actually, according to your bias risk, that might be, let's say the sequence B1 might be way better than the sequence A, which has highest probability. So yeah, once again, first problem is that sampling, grid decoding, and other decoding techniques, they do not guarantee us the optimal, the highest probability generation. And the second problem is that according to MBR, according to the bias risk, the generation might be not very, like according to the bias risk, you can have different, completely different perspective. What language model gives us is this probability distribution Py conditioned on the premises, the prompt, and what was generated so far. But what we care about, we might be caring about not particular realization of the text that we are generating. We're caring about some latent variable that specifies the semantic correctness of the generated text. We probably don't care about the synonyms that we're using during generation. Let's say we can generate, for example, for the question, what is the capital of France? We can generate Paris is the capital, or it's Paris, or the capital of France is Paris. So we can generate the answer in multiple different ways. And despite maybe the answer, the capital of France is Berlin, has highest probability according to our sampling algorithm. In fact, the probability mass for this semantic meaning that the Paris is the capital will be much larger. So that's another problem, that the probability distribution of a language model is not tailored for uncertainty quantification. The probability distribution for language model tailored only for generation, and we need to do a lot of things to make it more or less good for quantifying uncertainty of these generations. Right. So we are slowly moving to the real methods part. Just a few words what we want to discuss today. There are a few techniques for quantifying uncertainty. We can split them in two parts. First of all, we can think about one category of black box methods. Black box methods, they deal with LLM deployments that don't expose anything except for the textual generations. Let's say you have ChatGPT. It's a black box because you cannot reach the internal states, you cannot reach any logits. You need to do something only with what is generated by the model itself, like with the text that it generates. Second thing is consistency-based methods. These are based on sampling, and they look on how meaning of the answer changes depending on when you're asking the same question over and over again. There are also a category of white box methods where you have access to internals of a model or logits. And information theoretic methods, they use logits of a model. Unfortunately, most of the APIs currently do not expose logits, but if you're deploying your model through, let's say, VLLM, these approaches are way more informative than, let's say, verbalized uncertainty. And finally, there's like introspective techniques. These techniques, they analyze internal states of a model, and you can find some patterns. You can find some signals from this internal states, attention maps, that tell you that okay, this duration is a hallucination. Or you can even train some supervised probe on top of these durations. Yeah, also need to note that we can think about some hybrid techniques that can combine white box techniques, black box techniques. That combine different techniques such as information theoretic methods, verbalized uncertainty, consistency-based methods, introspective techniques. Okay, before we start moving actually to the discussion of methods, I would like to tell you that everything that I will be talking today in the second part is already implemented in our library called LLM Polygraph. So everything that you will see today, you can actually try it by yourself just by using our library. You can go through this GitHub QR code, and this library contains implementations of more than 40 or maybe already like 50 state-of-the-art methods that come from top-tier conferences such as NeurIPS, ICML, iClear. It supports all integrations such as VLLM, Hugging Face. It supports integrations with the services such as ChatGPT, Gemini, OpenRotor. It gives you a very useful extendable benchmark where you can that can be used to run research. And actually, many people from the conferences in LP and NeurIPS, when I come to their posters, they say, "Oh, actually, this work was done with the LLM Polygraph. We're really happy that we get that library." So if you're doing research in this area, I definitely advocate to try this library because you don't need to implement a lot of state-of-the-art techniques, and these methods which we have are have more or less clean implementation. All right, so yeah, just a couple slides showing how many methods we implemented. There are different types of different categories methods. There are some white box methods, there are some black box methods. Many of them are in our library, and here's a very small example, practical example, how you can integrate uncertainty in your code. I think it's pretty straightforward. You can see, yeah, it's pretty easy to add in your code. By the way, if you want to follow the standard transformer inference API, there's also even more natural way of integrating uncertainty within the class of your language model. So you can even make it even simpler than this example. Right, so the takeaways from this part is that we have two definitions of uncertainty. One is from the risk perspective, another one is from entropy of predictive posterior. There are two sources of uncertainty that people usually care about. It's aleatoric and epistemic uncertainty. Aleatoric is about like the noise in the data, and epistemic about the lack of knowledge about model parameters. If you think about that in a Bayesian way, Um, yeah, uncertainty for LLMs is way harder than for classification and regression because it has a lot of peculiarities. And yeah, we have a ton of techniques that we can already, even if you just give up right now on this talk, you can use many of these techniques from LM Polygraph without any knowledge of what do they do, how they work. The only thing I think would be important for you is to, at the end of this part, we will have a big recipe, which method to use in which situation. That will help you to navigate what uncertainty quantification method to use in certain situations. Right, so let's move on. I'm just curious, do we have any break or not, Alexei? Oh, okay, so we can just continue. Right, so, okay, let's maybe then continue, then we can probably have some more time for the questions. So first, this part, let's discuss the core uncertainty quantification methods for LLMs. First thing first, we can, with LLMs, as you probably realize, we can always ask LLM itself, how confident are you? Let's say we can prompt a model to provide some confidence estimate during the generation, or yeah, so we can basically ask a model to provide the estimate during the generation, or we can ask a language model to provide a uncertainty score after the generation happened. You can just feed what it generated back to the language model itself and ask, are you confident in what you just said? And as you probably understand, that if that would work well, that probably our job would be done and nothing really would be needed anymore. But hopefully for us as researchers, as scientists, this method doesn't really work well. When you're trying to prompt the model and ask its own confidence, usually it doesn't do any good job with estimating its own confidence. Actually, many people show that these estimates are completely discalibrated. Well, you can train the model in a certain way. You can do some alignment on top of the language model that helps it to be more honest with the user. But in fact, in most cases, the estimates that the model makes during the generation compared to the other uncertainty scores are completely discalibrated, completely disaligned. So once again, verbalized uncertainty kind of works, but usually it's way worse than anything that I will discuss later. You need certain post-training of your model to make this working. And third, yeah, so it's very, very overconfident. So another approach that is way more, that works way better. Actually, consistency-based uncertainty is one of the most performing techniques. The intuition is like this. Let's ask the language model the question, and if it answers the same thing over and over again, then it is confident. But if it starts changing its mind, you're asking, what is the capital of France? And it starts saying, oh, the capital of France is Lyon, the capital of France is Marseille, or it's Bordeaux. Then it means that the model doesn't really know the answer. It tries to just make a prediction of something more or less similar, more or less plausible. So when we have, when the model is confident, when we have low uncertainty, the answer will be usually the same. The Paris is the capital of France. When we have high uncertainty, the model starts changing its mind. Very simple approach. And one of the very simple techniques, but actually pretty good baseline, is frequency scoring. You can just analyze, let's say you have selected a certain answer of a language model to show it to the user, which is, here it is depicted as Y star. You can just count how many times other generations from the language model agrees with this generation. And that's actually a pretty good baseline, which is sometimes hard to beat. Another approach that would be a little bit more complex is to analyze the similarity of generated texts. As you can see, that there's multiple different ways of saying that the Paris is the capital of France. And the top three of these predictions are exactly about that Paris is the capital, but they all have very different realizations. You can see that they're all very, very different. But they all express the same meaning. And people realize that we need some measure of semantic similarity before we can say whether a model is confident or not. We cannot just, count certain answers. Well, probably when we have very simple answers, such as one token answers, we can do this. But when we are getting these long generations, even like for a few tokens, we already need some measures of semantic similarity to understand whether answers are actually the same or different. And here we can use different techniques from NLP. We can use techniques such as Rouge L, Blue Score, and LI to understand whether predictions actually mean the same thing or not. Yeah, well, from the risk perspective, if we define the loss in the way as like this, so we specify this loss as 1 minus similarity of our sample answer to the true answer, then we get a principled estimate of uncertainty through this through this risk function, through this loss function. Well, when we are getting this similarity scores between sampled answers, we can always build some graph of similarity between answers. In many cases, there'll be like situations when the model samples answers that are similar in one part, but are a little bit different in another way. So it not always it's not always possible to measure to have this binary decision whether two generations are similar or not. Usually, there's a certain degree of similarity between generations. So what you can do on top of the similarity approach, and on top of the consistency-based approach, you can build a graph, and then you can apply basically all techniques that you usually apply when you analyze the connectivity of this graph. I believe actually Alexei can tell you more about how these things work. Yeah, you can just analyze the similarity graph in multiple different ways. One of these approaches is, for example, using the graph Laplacian. It's one of the works that is actually one of the strongest techniques is eigenvalue method that computes the eigenvalues of the graph Laplacian that basically measures this graph connectivity. And this score will give you more or less good consistency measure. So once again, you can compute similarity of your predictions of your samples to each other, create a graph, construct graph Laplacian, and then analyze this graph Laplacian in multiple different ways. One of them is using these eigenvalues. All right, so that was consistency-based approaches that try to understand whether the model generates the same thing over and over again or not. Another approach, of course, and these techniques, they completely ignored the fact that our LLM can approximate some probability distribution for our tokens. And of course, this information is very, very important for us. One of the best, I think, one of the best straightforward approaches, very good baselines, is sequence probability. Well, sequence probability is very simple to compute. You just take the token probabilities and multiply them. But usually, of course, you're computing the logarithm. You have not probabilities, you have logits, and you have it's easier to get the log probabilities rather than the probabilities. So people usually compute this minus sum of logarithms of probabilities, and that's actually a pretty good uncertainty score. Very good uncertainty score and very good baseline, which is very hard to beat. Well, one of the problems with this technique is that it has natural bias towards shorter sequences. Of course, shorter sequences have smaller number of tokens. And of course, they will be much, much more probable because the probability of each token is very small. So people try to somehow fix this bias. And one of the techniques that helps us to fix this bias is perplexity. It's basically a length normalized log probability, which kind of tries to mitigate this bias. Unfortunately, despite the fact that, well, we are trying to correct something here with perplexity, but in fact, what we observe in real situations is that perplexity sometimes works worse than sequence probability in general, because this bias actually helps us usually in real-world tasks. So none of these techniques are actually like perfect. All of them have, every time you're solving your own task, you have to look into the metrics. And maybe in some cases, this bias is important. In some cases, this bias is not very useful. And actually, one of the work that of our colleagues, Maxim Panov and Roman Vashurin, they investigate this problem in this paper, Uncertainty Line. They show that in some situations, it's better to subtract this bias towards shorter sequences, or they show a way of correcting this bias in a better way than in perplexity. Right, so what are other things that we can do with our logits? Well, we can compute something like mean token entropy. Well, each duration of each token is a decision, and we can compute entropy for this decision, and then we can somehow aggregate this entropy. There might be different ways of aggregating entropy. You can take the maximum, you can use average. Here, for example, we can use average, which leads us to the mean token entropy. Also, pretty good approach, which is usually a good baseline, but once again, very, very simplistic. So what the problem with this mean token entropy is that, and like in general, sequence probability is that they do not account for the fact that probability distribution of a language model is not tailored for estimating the quality of the generation. I mean, it is tailored for generation, but according to our standards, according to our perception of what is hallucination and what is not, whether the generated text is credible or not, it's doing pretty badly. Here is an example. Well, you can ask a language model, when and where did COVID-19 start? And the model can generate you a text. The COVID started in December 2019 in China. But it also can do this in reverse. It can generate the text. It started in China in December 2019. So you can see it can swap the claims. It can swap the order of the claims. The problem is that the uncertainty about which claim to generate it's encapsulated in the log probabilities of a language model. So this y condition on the context, it contains a lot of redundant uncertainties that are not particularly relevant for the task of hallucination detection. So on the left side, we see that it contains information, it contains uncertainty about what fact to generate first. The time of the pandemic start or the place of the pandemic start. On the second part, on the right side, we can see another example that you can, let's say, you are asking like, I don't feel well, what would you recommend? And the model answers, I recommend seeing a doctor, but it can also specify, instead of doctor, it can also say physician, right? So it can use multiple different synonyms to relay the same meaning. And the uncertainty about what synonym to use is once again in this probability distribution. So maybe if you look into the log probabilities of this distribution, you will find out that the model is very, very uncertain. Like 50% doctor, 50% physician. That's, you know, that looks like model doesn't know what to say. But in fact, doctor and physician is the same thing, right? So the model is very, very, very confident. So if we would rely on these probabilities, we would be doing, so if we would be relying on these probabilities, sometimes we'll be very, very underconfident. All right, so just a few words about one of our methods that we recently, well, not recently, but published some time ago. We try to correct the probability distribution in the way that we remove uncertainty related to synonyms, and we remove uncertainty related to the order of the claims that we generate. So we basically analyze the options that the model might generate and split it in three parts. The options that have the same meaning, that lead to the same meaning, the options that are contradictory to the originally generated meaning. Let's say here we are having, let's say, for example, we are asking the model like about some person, and model generates, he died in a plane crash in 1928. And you can see there's like multiple options here. There's options that are 1928 is exactly what we are showing to the user. But there are other options which are 1930, 1929, 1933, and there's also option Norway. So the model might choose to generate the date when somebody crashed or the place when somebody crashed. And you can see that these options are contradictory, and this one is completely relevant to our original generation. So what we suggest to renormalize the probability distribution in a way that we completely ignore options that are not semantically related to our original generation. So we take our original probability distribution, we sum probabilities of all options that relay the same meaning, and we normalize them on the probability mass of all options that entail the same meaning or contradictory meaning, completely ignoring options such as like the yellow options such as Norway that are not related to our original prediction. So there's a certain principled explanation why this is actually a correct way of quantifying uncertainty in the paper, but yeah. So in this case, we try to alleviate uncertainty that is encapsulated in original distribution of a language model. So we extract, we alleviate two types of uncertainty, which is one of them related to the synonyms to choose, and one of them is related to information, the order of claims or like the type of claims that the model wants to relate to us. Yeah, and particular how we're doing this, we use NLI model, but once again, the details better to look into the paper. Well, another problem that we have with uncertainty quantification when we are dealing with generation, with language models is that not all tokens actually contribute equally to uncertainty. Let's say here is an example where we have lots of auxiliary words such as articles, prepositions, and other things. And one of the ideas recently that was proposed is to try to alleviate the impact of these tokens and focus mostly on tokens that actually carry some meaning. Here we see that most important parts are like Donald Trump, the answer, like who is the current president of United States? And we can see that the most important part of this answer is actually the name of the president, while all other tokens are marked as less informative. So how people can do this? Well, first of all, of course, you can assign some weights to the tokens before you aggregate them into uncertainty score for the whole sequence. There are a few ways to do this. One of them is through, let's say, analyze scores. We can, let's say, remove certain word and see how the meaning of the text changes. This method is called tokensar. Another option would be to use some named entity extraction. But, well, in general, the whole concept, the whole idea of this approach is to assign certain weights to the tokens depending on how important they are for the meaning of the sequence. And usually this adjustment gives you some improvements for your final performance metrics. Okay, so we dealt with methods based on uncertainty quantification, based on the logits, based on the information theoretical principles. They are very good. Actually, they're good baselines, but these techniques usually cannot. One sample from the language model doesn't give you a lot of information. I mean, it gives you information. Once again, there's logits. But at the same time, when you do multiple samples from the probability distribution, you can explore this probability distribution much more comprehensive way. And that's what people try to do. They try to sample multiple generations from the language model and try to analyze the probability distribution according to the sampling techniques. One of them, well, of course, you can simply just sample multiple generations of from the language model and analyze the. You can basically construct all information-based methods in the same way as we discussed before, but aggregating multiple predictions according to different samples, which gives you something like Monte Carlo sequence entropy techniques. But once again, and you can also try to do some, let's say, length normalization and other things. But what really works better is something like semantic entropy. Actually, semantic entropy was already discussed during this school before. Idea is that we need, once again, to deal with the problem that LLMs, they generate the same meaning in multiple different ways. And to understand the, let's say, the probability of certain meaning, we need to somehow aggregate this probabilities of different sequences that have the same meaning. And the very simple idea that was suggested by a group of Yair and Gal, which is one of the seminal works in LLM uncertainty quantification, which was published actually in Nature, they suggested to do some hard clustering of your generated sequences. Let's say you have, you can see that there are a few answers that the language model has generated, and when we are asking it, like, what is the capital of France? There's like, Paris is the capital of France, France is the capital of Paris. And you can put different, you can do this clustering, and you can compute the probabilities not just for individual generations, but you can compute probability of individual meanings. And then what you can do, you can compute entropy on top of these meanings. This method works more or less well. It can be considered as some sort of a more sophisticated consistency-based technique, where you are, in consistency-based techniques, you're mostly trying to understand the similarity between different answers. And here, you're trying to understand both the similarity of different answers, plus you would like to understand what was the probability mass assigned with certain different predictions. Well, unfortunately, semantic entropy, while it is one of the seminal works and pretty good method, it lacks one it has a lot of issues. One of the main issues of this semantic entropy method is that it lacks it doesn't take into account what generation you have sampled. As you can see, in semantic entropy, you're just you don't have any information that comes from the answer that you're showing to the user. But in fact, you can sample any answer, and this answer might be actually pretty bad. And there's no way to actually relay this information in the method. There's no way you can actually demonstrate, incorporate the credibility of answer that was specifically shown to the user. So here, this method quantifies uncertainty, but it, as I already told you, what we really care about in hallucination detection, we're caring about the risk that is assigned with particular answer that is shown to the user. So to correct this problem, one of the papers that we are has been delivering, we delivered at NeurIPS 2025. It's our attempt to combine consistency-based techniques with information-based scores. Here we, basically the idea is very simple. We just multiply some information-based metric with consistency-based score. And consistency-based score is basically sum of similarity of our, it's computed through the similarity of our generation that we show to the user compared to other the other samples that we have during generation. So what we have here, we have component that is responsible for understanding how different are the answers according to the whole generation, and how credible is the answer that we particularly showing to the user. So that's why this actually method, this cocoa method, works way better than let's say semantic entropy. So because it takes into account the spread of the distribution and the credibility of particular answer, the confidence of particular answer. Yeah. When we are, that's actually another another follow-up of our paper was that we found an important thing is that if we apply beam search on top of the generation process, like we can do actually way better. We can, if we are sampling randomly from the distribution, usually, sometimes we're actually getting the realizations that are semantically not very diverse, or sometimes we get the generations that have very low probabilities. We have low probabilities. How we can correct that? We can use beam search. Beam search gives us actually pretty diverse generations. And at the same time, the probability mass of the generations will be pretty high. And applying it on top of the cocoa, let's say you are having just this method where we have, when you sample multiple generations, you multiply the consistency score with the uncertainty score for the particular shown generation. actually, beam search helps you to improve that a little bit. And we show that if your beam search recovers, let's say, a big chunk of this probability mass that you have in your distribution, then actually that gives you a benefit compared to the basic methods. Yeah, one of the problems with consistency-based methods and methods based on like any sampling-based technique is they're very, very inefficient. So every time people tell me that certainty score that we are using, like semantic entropy, or let's say anything from consistency-based approaches, the problem is that when you sample 10 times, to make this method working, you need 10 samples. And sampling 10 times, it basically makes your generation way, way slower. You're paying 900 percentage points to quantify uncertainty, which usually is not efficient. The only time when these techniques are actually useful are situations when you already have to sample. Let's say if you're already using a beam search, then our method, COCOA method, based on sampling, it's basically a free lunch. So you get both the good generation and the good uncertainty score. But there is a case where these sampling-based approaches are actually can give you like the good uncertainty score without any loss of efficiency. And that's the case of diffusion-based models. In diffusion-based models, as you know, you have a trajectory of like multiple samples from the language model. So you can reuse the samples to quantify uncertainty. So every time you have a diffusion-based model, you can have both fast generation and good uncertainty score. And in our recent preprint, we show that this trajectory is pretty good. It can recover like 95% of what you can achieve using the straightforward, the approach with the consistency-based techniques. So yeah, one of the approaches that we recently proposed is DCOCOA. It's basically the same COCOA method where we replace the component related to consistency using the trajectories that we generate using the trajectory, using the samples from the trajectory that you generate through the diffusion process. And the second thing, we replace the maximum sequence probabilities estimate with the estimate that is more tailored to the diffusion-based models, because of course diffusion-based models don't have this factorization of probabilities as you have in autoregressive models. Right, so for this part, takeaways are the following. So we can tackle the uncertainties quantification problem from multiple perspectives. We can first ask the language model itself, are you confident or not? Usually it's not the great way to do this, to quantify uncertainty, but in some cases it's the only way to do that, especially in the black box scenarios. Sometimes it works when the model is trained, when the model is aligned to be honest, but that's actually a big part on its own, big research direction on its own. Second thing, you can use consistency when you can ask the model multiple times the same question and analyze whether it changes its mind or not. That's called consistency-based techniques. They are kind of good. They kind of gives you more information than verbalized techniques, for example. But once again, you're paying some price for that. You're paying time. Unless you're doing already some sort of beam decoding, consistency-based techniques are actually quite slow. Information-based methods, they are actually good baselines, and in many cases you can use them for practical purposes, but unfortunately these techniques cannot explore the probability distribution in the same way as you have with the sampling-based techniques. And finally, the hybrid techniques that combine consistency and confidence, actually one of probably the best way to go, especially if you're already doing this beam search. then it's essentially free for you. If you're having a diffusion-based model, that's once again, that's free for you. So this hybrid techniques, this COCOA technique applied to on top of the beam search or on top of the diffusion-based model is one of the, I think, the best methods to quantify uncertainty in an unsupervised way. All right, just a few words about introspective and supervised methods. Okay, introspective methods. I believe that Alexei will talk way more about that, but I just want to say that when is it the only way to quantify uncertainty? Only to pay price for sampling, or just have some underperformant information-based techniques? Actually not. When we are generating, there is a lot of information that is stored in hidden states or attention maps of a language model. And we can harness this, harvest this information to build a pretty good uncertainty estimates. In one work, we analyzed the attention weights of a language model. We specifically looked into attention weights from our currently generated token to the previous one, and we looked into some correlations. And we realized that usually, actually, there's no correlation between attention weight and presence of hallucination. We can see the majority of the attention heads in our language model, they completely ignore the presence of hallucination. But there is a very small number of attention heads that express certain high or low positive or negative correlation with the presence of hallucination. And that's actually quite important informative signal. So we can use these heads to quantify uncertainty. So I believe that attention weights have a lot of information about presence of hallucination. Once again, I think Alexei will discuss that in more detail. I will skip this part that attention can be proxy for understanding the conditional dependency between generation steps, and you can leverage that to improve your uncertainty scores as well. Yeah. One important, once again, I would like to say a few words about our ICML paper, which was presented back in Seoul 2 weeks ago. It's about attention patterns. Exactly what we did, we looked into attention weights and found certain patterns that correlate with the presence of hallucinations. And here's one of those examples. You can see that here's a generation of a language model, token by token. And on the x-axis, there's a attention to the previous token for different attention heads. And here is like the green words are correct words, and the red word is the hallucinated word. And you can see there's a certain head here that has commonly pretty high attention to the previous token. But when we are generating a hallucination, the attention blurs. So that's one of the patterns that we found in attention that led us to the very simple technique that that gives us pretty good results for the single generation of a language model. So we don't need any sampling. We don't need any large overhead. We just use this attention pattern to find hallucinations. What we do, we search for attention heads with a most contrastive signal. We exactly try to find this attention head with the most informative behavior for hallucination detection. That is automatically, completely unsupervised way. Then we compute a recurrent layer-wise confidence score, which basically integrates confidence estimate on the current generation step plus the confidence that comes from the previously generated tokens. That's actually, this second step comes from the fact that generated tokens are conditionally dependent. And finally, we aggregate them into the layer-wise uncertainty score to assess the final credibility of the generated text. Yeah. So once again, we have a pretty good method. Sorry, shameless plug, but in general, I think works pretty well. And also a few words about training-based techniques. Actually, if we have some patterns, what we can do, we can not try to try to find these patterns by our own. We can just train some models that can help us to detect hallucinations, right? What we can do, we can generate some text from the language model. We can label each text, or maybe some spans or segments of text, then we can engineer some features. Maybe it will be hidden states, hidden activations, maybe attention maps. And we can just train simple hallucination detectors, which will be like very lightweight transformers, or maybe it's just a linear probes, or maybe it might be MLP. And actually, that works pretty well. This technique, despite the fact that you are training like external model, it still uses internal representations of language models. So we are not introducing external knowledge. We're harvesting the information that comes from the language model itself. So we can still claim that it's some sort of a form of confidence estimation or maybe uncertainty quantification. Yeah, simple techniques that appear like in 2023 just use some hidden states from the last token of the prompt, or like the first token of the last token of the generation, built a very simple MLP classifier in that, and actually, surprisingly, that worked pretty well. The follow-up works use some engineering top of the attention maps. They look, let's say, how attention is spread between the tokens of the generations and the tokens of the prompt. And finally, what we did, actually, the last year, we created a library that allows you to build this hallucination detectors on top of the language model internal states, which I think it's a go-to for supervised hallucination detection methods. Yeah, very straightforward code. If you would like to, let's say, introduce, so this uncertainty quantification head is like additional head on top of the language model, which is, once again, a very lightweight transformer, only like 10 million parameters or maybe 100 million parameters. That helps you to detect hallucinations in the text, and it's pretty good. It generalizes well across domains, it generalizes across languages. We have a Python library for that. Yeah, please check it out. And if during the inference, it's very easy to integrate this uncertainty head in your generation pipeline. You just create a wrapper, and you generate the same way as you done originally with your Hugging Face API. So takeaways. From this part, introspective methods, we can do still pretty well if you don't have any samples. We can leverage internal signals from LLM, and we can extract some valuable insights from the language model. Attention matrices is a very golden mine for researchers. I think there's still a lot of information stored in attention matrices. Supervised methods can help us to drastically outperform unsupervised techniques, and they help us to deal with uncertainty quantification in more or less narrow domains. So if you have like a narrow domain, let's say medicine or maybe a law, then I believe it's possible to train more or less good hallucination detector that will be way better than anything that you can think about from the supervised point of view. Yeah, we have a framework that is compatible with LM polygraph for, first of all, like all methods that we have presented today are in LM polygraph, and even supervised techniques that we are promoting, I was promoting in the end, can be also integrated in LM polygraph, and we have a library for training these hallucination detectors. Yeah, just a few words, final summary for uncertainty quantification. So that's a recipe, universal recipe for your universal recipe for how to deal with uncertainty in LLMs. So if you have, let's say, ChatGPT, you have black box LLM, and you don't have compute budget. Let's say you have only budget for one generation from LLM. Then there is no other way just to ask language model directly. It's verbalized uncertainty scores. But these are not very good. Usually they're terrible. So if you have compute budget, then consistency-based techniques are your friends. You can sample multiple generations and analyze how how consistent is the model during the answering the same question over and over again. Well, if you're not black box, but you have access to some logits, when you can do much more things on top of your consistency-based techniques. First of all, if you have budget for compute, then you can do some sampling. Or if you're, let's say, already doing beam search, then you definitely need to go for the COCOA method that we presented at NeurIPS. If you don't have any compute budget, then, well, maybe information-based techniques such as MSP are not bad. They're good baselines. Once again, they're probably better than verbalized uncertainty scores. If you have access to the full model, let's say you're not using ChatGPT, but you're deploying your own LLM on your hardware, then probably you have access to the internal states of a language model. And if you have some annotated data, then probably the best way of doing uncertainty quantification is training some of the supervised methods, such as uncertainty quantification head that I presented before. And if you don't have a compute budget, then if you don't have analytic data, then once again you can, and you have compute budget, then you can go back to COCOA and hybrid techniques. Well, that's probably the best method in general, especially if you have beam search. And if you don't have compute budget, you can try these introspective-based methods based on attention patterns that probably give you some improvements. Once again, in LLM polygraph, you can integrate uncertainty in this very simplistic way. And yeah, there's actually a huge part about agentic and reasoning. Of course, cannot discuss that. But in general, what my claim to take would be that uncertainty nowadays is not just a guardrail anymore. Uncertainty can help us to improve the performance. It can help us to improve the efficiency of our agents. And that's a lot of material. If you want, you can check it out after the session, or talk with me. After that, the main thing is that we are trying to facilitate actually this research direction where we are using uncertainty not just as a guardrail, but actually as a tool that helps us to improve the reasoning, improve the agents, and few directions that we are currently looking into. That's agentic workflows where we are trying to assess uncertainty of tool usage. We're trying to assess, we are trying to use uncertainty as a channel of integration between agents. And currently, agentic applications of uncertainty, I think it's way under investigated right now. So we have a lot of low-hanging fruits over there. Second thing that we're investigating is, of course, we are trying other modalities. And the third thing that we are investigating right now, we are trying to understand whether we can do alignment of a language model, whether we need any uncertainty on top of that. So once again, we can try to train the model, so to be honest, right? The question is like, do we need anything on top of that? And right now, my intuition says that actually uncertainty will still be a useful technique, even if we post-train our model, to be honest, because post-training usually do not deliver such good results as what we expect. And moreover, we can do something on top of that all the time. Yeah, so final takeaways. Machine learning models will be always limited due to two factors. The limited amount of training data they are trained on, and ambiguity of our tasks. And uncertainty is a crucial component of any machine learning system in general, including the one based on LLMs. And of course, it's crucial when you have high-cost scenarios, such as healthcare or finance. We have a framework for uncertainty quantification, LLM polygraph. Everything that I talked today, you can directly apply in your code by using LLM polygraph. There's a practical examples in the framework. You can do some experiments with LLM polygraph. In general, uncertainty is a fascinating research direction. And I think we have so many low-hanging fruits in reasoning, LLMs, and agents. So yeah, please consider, joining this interesting direction. We'll be happy to collaborate. Yeah, just a small announcement in the end. Yeah, we have MBCY is a pretty good university. Yeah, try, consider applying for a PhD or master students. Unfortunately, I have to make this marketing because we are. Because marketing people ask me to do this. And finally, a few links. Here's a tutorial at ACL in 2025. If you're interested in uncertainty quantification, I tried today to make this compressed discussion of this tutorial, like of this 4-hour tutorial, in very short period of time. But I believe if you would like to have a more in-depth explanations of uncertainty and how to quantify it, how to detect hallucinations, go there. Our library LLM from GitHub, and also our paper, tackle paper, which has a pretty good overview of uncertainty quantification methods in general. Right, thank you very much. And yeah, sorry for...
Yeah, it's working now. Thank you for your talk again. And I wanted to ask you about this hypothesis that there might be examples of hallucinations that cannot be solved by... Actually, I got confused in the middle. Do you think that there is no universal uncertainty quantification or hallucination detection method? Maybe for every method there is an example that it cannot catch.
Yeah, thank you very much for the question. Actually, if you look into our papers, in any paper actually, you realize that the performance of uncertainty quantification method, even if people claim that it's like the best overall, you look into different data sets and you see that the performance depends really on the data set, on the task, on the model that you use. And that's actually very related to the fact that certain models, let's say, better approximate the true distribution. And as I showed, that certain theoretical definitions of uncertainty, they're actually very connected to the fact that our approximation of the true distribution should be good. So my third on that is we probably can get a good uncertainty quantification method for certain domains. If you're, let's say, working with in medicine, well, training like a probe on top of the internal states of a language model, on top of the attention maps, will probably give you a pretty good uncertainty score. And probably it will give you the upper bound of what you can get from this general approach. Once again, uncertainty is what we are thinking about. When we are thinking about uncertainty, we're trying to leverage as much as possible the capabilities of a language model itself. But of course, there is a certain ceiling there. You cannot go past the ceiling. And I believe that training-based techniques, that's the upper bound that we can achieve in general. But yeah, at the same time, if you're having more or less well-defined domain, you can engineer a pretty good hallucination detector for that, and that'll be a great contribution to the overall generation of LLM. You can use it for the final users. You can maybe try to use it as a filter of incorrect generations. You can use it for reasoning, for improving the performance of agentic workflows. Actually, you know why? Uncertainty, why we started focusing on agents and efficiency of reasoning is that there in reasoning and agentic workflows, it doesn't really matter like if your uncertainty doesn't work all the time. And that's true. Uncertainty scores cannot give you magically that this generation is correct, this generation is incorrect. Usually you have the scores are like in 60s or 50s or maybe 70s at maximum. But that's more than enough to improve reasoning performance, because if you're choosing the better reasoning path, like in more cases, then you get better reasoning performance. If you're, let's say, avoiding computation of additional tools, like 40% of the time, you're saving a lot of tokens. So I think that actually fascinating area of application of uncertainty is for this areas where it shouldn't be perfect. It should be work better than random, and it will still give you a huge amount of benefits.
Thank you for the lecture. I have maybe a relatively simple question, but when it comes to annotated data sets of hallucinations, we have to somehow figure out what is hallucination and what is not, as probably we want our data set to be big. So probably it is hard to annotate this just using human resources. So we need some sort of automation. And how exactly like the best data sets in the field are collected then?
Yeah, thank you very much for the question. Actually, a very good question. Indeed. Well, I don't agree that it should be like large data set. I think if you're dealing with in-domain hallucination detection, you can do more or less well with just as like 10,000 predictions, maybe 5,000 predictions will be already enough to train something. I think the more data, the better. You have better generalization, and with more data, you can use something like hidden states, like hidden activations. Attention maps usually better for not overfitting, but if you have a lot of data, you're not overfitting anyways. All right, so how to collect data? Yeah, indeed, there are many ways to do this. Actually, you can leverage some, let's say, another language model. One of the good examples, for example, our another paper that got oral at ACL. Actually, I've been not just to ICML. I went to San Diego, then to ICML, then here. At ACL, we got a paper where we were using a reasoning language model to annotate its own reasoning traces. So we run the language model, the full reasoning trajectory for each reasoning step. Let's say we're solving a mathematical task, and we ask the language model, do you think that this reasoning trace was good? And we run it for another, like, let's say, 2,000 tokens. And because we are running it for a pretty long time, it actually creates a pretty good annotation of its own reasoning trajectory. So it's like self-supervised annotation. But what we are doing when we are training hallucination detector, we're basically distilling this huge reasoning trajectory into very small uncertainty head that uses internal states. So that's still beneficial. So yeah, one way of creating annotation is self-annotation, especially with reasoning models that gives you pretty good results. But another option is just use, let's say, a committee of models, or yeah, using even like if you're dealing with a smaller models such as 8 billion or 10 billion parameters, you can always use something more sophisticated such as ChatGPT and basically distill the knowledge of ChatGPT, what is hallucination or not in these probes. Another option people also use is they just create artificially hallucinations, but I think that's not a good idea because the best way of creating the data is created on policy, which means that you're annotating the data that was generated by the language model itself, because then you're not, yeah, that's the best option. That's the data is not artificial.
Thank you. Thank you.
Thank you for your presentation. I got a question about the hallucination. So mainly it is because of the uncertainty, right? But if we train the model and if we feed the model like uncertain data, and if our data set is not so good, maybe it learn from this uncertainty, and how can we like reduce this kind of?
Yeah, and our uncertainty quantification model will be uncertain. That's a great question, actually. That's something that I want to always investigate. You know, if you're training your uncertainty probe on some data set, you will get another model, and this model can be confident or not. And you can probably create some sort of a fallback mechanism. Let's say if your uncertainty estimation module is uncertain, then you fall back to something unsupervised estimator, something like maximum sequence probability or the mean token entropy or perplexity. And if your uncertainty estimation model is confident, then you're probably in distribution and you can do more or less well for estimating the confidence of the model. So I think that something like hybrid, something like this would be pretty good recipe.
Okay, thank you.
Yeah, thank you. Yeah, thank you very much.